Hello, everyone. The next talk is by Dr. Neha Malik. She is a postdoc at Chennai Mathematical Institute, and she will be speaking on the subalgebra of Stiefel-Whitney classes for finite symplectic groups. Over to you, Neha. Please begin.
Yeah, hi. Hello, everyone. Thank you all for joining from all over the world. So let me start by covering all bases by saying good morning, good afternoon, or good evening, whichever applies to you. And I would like to thank the organizers also, and especially Soumya for the invitation. So, as said, today I'll be speaking on the subalgebra of Stiefel-Whitney classes for finite symplectic groups. So the calculation for these characteristic classes begin during my PhD, and with time we continued working on this, and we have come across some very interesting consequences of our calculations, and you'll see one of that in this talk. And this is joint work with Professor Stephen Spallone. So let me begin by saying what these classes are and some of their properties. Yeah. So classically speaking, Stiefel-Whitney classes make sense for any real vector bundle. So if I wanted, I can completely change this talk into a completely topological one. But for today's talk, I'll stick to the representation theoretic part of my work. So let's start by saying what these classes are. For this, let's take G to be any finite group, and let's take pi to be any orthogonal representation of G. Then we can associate to pi certain cohomology classes, which we are denoting by Wi pi, which are Wi pi is an element of ith cohomology group with Z mod 2 Z coefficient, and there is a whole sequence of them going starting from 0, 1, and so on. And these classes, we call them as Stiefel-Whitney classes associated to pi or of pi. Now we can also form their sum, and we call it W pi, and that this sum turns out to be an element of the whole group cohomology ring, again with Z mod 2 Z coefficients, and this sum we call as a total Stiefel-Whitney class of pi. Now let's look at some of the properties of these classes. The first one is that the zeroth Stiefel-Whitney class of any orthogonal representation, it is always 1. The second one is that we all know about this well-known isomorphism between group of Homs from G to plus minus 1. And this is isomorphic to the first cohomology group of G. And here, from now, the coefficients are always Z mod 2Z. So I'll skip writing it again and again. And I'm saying that W1 acts as a function on these. So the group of homomorphism from G to plus minus 1 can also be thought of as the group of one-dimensional orthogonal representations of G. So, and if you apply W1 on such a representation, then you get an element of H1, as we saw in the previous slide. And in fact, this turns out to be an isomorphism. The third one is that if you take any I, which is greater than the degree of the representation that you started with, then for all such i's, Wi pi is 0. So that makes this sum that we had, W pi, this is a finite sum, and so it makes sense to write it like this. So that this becomes an element of the group homology. Coming to the next property is that these classes are natural. So here, that means that if you are starting with two groups, G1 and G2, and you have a group homomorphism from G1 to G2, and let's take an orthogonal representation of G2, then by composition of pi and phi gives us an orthogonal representation of G1. And we can get the total Stiefel-Whitney class of this composition from the total Stiefel-Whitney class of the representation that we started with the help of this map phi star, which is simply the map induced by phi at the level of cohomology, the pullback map. And the last property that I would like to mention is that if you take two orthogonal representation, form their direct sum, then the total Stiefel-Whitney class of this direct sum is simply the cup product of the individual total Stiefel-Whitney classes. Now, these properties altogether gives an axiomatic definition of these Stiefel-Whitney classes and also give their uniqueness. So you can take these properties as the elements of the cohomology groups which satisfy these properties are called Stiefel-Whitney classes. Now, moving on, the question that we first started dealing with was that if you are given a finite group, then what do we want? We wanted to find an explicit formula for the total Stiefel-Whitney class for any orthogonal representation in terms of character values. So I'll explain what this phrase in terms of character value means as we see one of such formulas. And we answered this question for all these following groups. So the simplest one was SL2Q for all finite symplectic groups, SP2NQ for Q odd. For finite special linear groups, SL and Q, when both N and Q are odd, and also dihedral groups, which are basically orthogonal groups O2Qs. Okay, so let's first see one such formula for this our simplest group that we dealt with, which is SL2Q. And let's take Q to be odd. We have the formula for Q even too, but here I'll stick with Q odd throughout this talk for the rest of the talk. So let's Q to be odd, and our G is SL2Q. Now, the fourth cohomology group of SL2 is Z mod 2Z, and let's denote the non-trivial element by E, by this frac E. And the formula that we got for the total Stiefel-Whitney class of any orthogonal representation of SL2 is this, simply 1 plus E to some exponent R pi. And we express this exponent in terms of these character values at the identity matrix and minus identity matrix. So this is what I meant by when I said in terms of the formulas are in terms of character values, that whenever there is an exponent which was involved in the formula, we have given a character value formula for those exponents, and the character values that appeared were at diagonal involution. So they were quite simple in that sense. Okay, so once we had this formula, we tried to answer some questions that were asked. Like, let me state this question. This was asked by Professor Dipendra Prasad. Let's take a group and all the orthogonal representations of that group, and then find all the Wi pi of Wi pi's and take the subalgebra generated by all these individual Stiefel-Whitney classes. And we denote this subalgebra by H star SWG. And we want to understand what this H star SWG is. So the question that Dipendra Prasad asked was that is it true that if you take such a subalgebra, if you take the subalgebra generated by these Stiefel-Whitney classes, does it always turn out to be the whole group cohomology ring? And the SL2 itself gave a negative answer to this question. And so here, for the reference, it is already known that for SL2, its group cohomology ring is tensor product of one polynomial algebra and an extrinsic algebra. So this was degree 4 and this is degree 3. And if you look at the formula, it is clear that this part doesn't appear at all in the formula. So it is clear that H star SW is not equal to the whole group cohomology. But we still want to understand what exactly is this H star SW is. So for that, what we need to understand is this R pi. So what are the values this R pi can take? So is it always for example, is it always even? Is it always divisible by some other prime? Or is it always 0? It can always be 0. So that all the Stiefel-Whitney classes basically turn out to be trivial. So we want to understand this R pi, and with the help of that, we can understand what kind of Stiefel-Whitney classes appear in H star SW, what generates this H star SW. So for SL2, we used a result by Argao in one of his paper in 1984, where he characterized the orthogonal or symplectic representations for finite symplectic groups. And his result for SL2 translated into that if we start with a self-dual irreducible representation pi of SL2, then it is orthogonal if and only if -1 belongs to the kernel of pi. So if you think of it in terms of character values, that just means that chi pi at minus identity is same as chi pi at 1. So basically that says that r pi is 0 if, okay, wait. Yeah, r pi is 0 if the pi that we are dealing with is irreducible orthogonal representation. So W of pi is simply 1 for all irreducible orthogonal representations for SL2. Okay, so now from irreducible orthogonals, we didn't get anything. They don't contribute to H star SW basically. Now, what are other kind of representations that we can play around and see and get more information about this R pair? So the another class is something that we call orthogonally irreducible. So for that, what we do is we start with an irreducible non-orthogonal representation of the group. And we form this direct sum. We take the pi and we form its direct sum with its dual. So this S pi becomes self-dual just by the construction. But in fact, we can also give a G invariant non-degenerate symmetric bilinear form on the vector space corresponding to this pi, which makes this pi an orthogonal representation too. Okay, so these are another kind of representation that we can play around and see that the Stiefel-Whitney classes of such representation, are they coming out to be something non-trivial? Are they contributing something non-trivial to H star SW? So in particular, if we take pi to be irreducible symplectic, then simply by the result by Argao, we can, so from Argao, it just simply said that chi pi of -1 will be simply minus of chi pi of 1. And if we substitute that, this is what we get. And SL2, because it's a nice sort of group and we understand its representation theory, we know its we know its character table. So we know that it has irreducible symplectic representations of degree q plus 1 and q minus 1. So the representations of degree q plus 1 which have these properties are the ones which are parabolically induced. So if you take any alpha, which is a linear character of fq cross, and satisfies these properties, this then basically FQ cross is the diagonal torus for SL2. Then you can inflate it to its Borel and then you induce it to the whole group. And the representation that we get, we call pi alpha, corresponding to this alpha. And if this alpha satisfies these properties, the associated pi alpha turns out to be irreducible symplectic. Okay, so this condition is related to irreducibility, and this condition is related to makes it symplectic. Okay, and these have degrees q plus 1. Similarly, if you see the irreducible cuspidal representations of SL2, they have degree q minus 1, and we know that irreducible cuspidal representation of SL2 are associated to linear characters of FQ square cross. And again, if you put these conditions on this linear character theta, the corresponding pi theta that we obtain will come out to be irreducible and symplectic. So by combining these two, what we get is R of S pi alpha. This is the parabolically induced one. We get this to be q plus 1 by 2 and R of S pi theta to be q minus 1 by 2. And depending on, because we had started with q odd and now we can again divide it into two, depend q is 1 mod 4 or 3 mod 4. One of these is odd. Okay. And now if you just remember the formula for W pi, that was simply 1 plus E to the R pi. So the coefficient of, if you just expand it out, then the coefficient of E is simply R of pi. And if this is odd, that means that E is the fourth Stiefel-Whitney class for one of these representations, depending on whether Q is 1 or 3 mod 4. So combining all this, what we have, we can say is that H star SW of SL2 is this whole polynomial algebra with the generator with E as the generator. Okay. So moving on, we also try to do the same thing for SP4Q, but with SP4Q, it becomes difficult because again we don't have that much knowledge about its representations, and we know the character table of SP4 given by Nivasan, but it is very difficult to understand. There is the character table, but if you want to understand to what kind of representation though that character table, the characters in that character table associate to, it becomes much more difficult. But somehow it we turned out to be lucky, and we got something nice, and we found out H star SW for SP4Q too. So first, let's look at the formula for the total Stiefel-Whitney class for SP4. So in general, we have obtained such formula for SP2N, and here from that generalized formula, I'm just taking out what it says for SP4. So let's take D1. D1 to be this diagonal element, minus 1, 1, 1, minus 1 in SP4. And then, and if pi is an orthogonal representation of SP4, then the total Stiefel-Whitney class of pi is given by this formula. Now, these EIs, E1 and E2, they also have, these are certain elementary symmetric functions in another frac E1, E2. So, but I'll not go into that for the time being. We can just you just take this as a formula, and again the exponents that we have, we have given character value formulas for these with the character values at the values that we have considered are at 1 at identity, minus identity, and this diagonal element which is an involution, a D1. Now, from this, it is clear that if we want to, that H star SW of SP4, it is inside, okay, wait, it is inside this Z mod 2Z E1, E2. But what we proved is that it in fact is exactly equal to this polynomial algebra, again with two generators, E1 and E2. And for the proof of it, again, what we so SL2 is kind of the base case. If we developed it step by step to get SP2N, and that again was done with the help of this subgroup. So inside SP4, there is a subgroup X, which is isomorphic to SL2 cross SL2, and it sits like non-zero entries are only on the diagonal or on the on anti-diagonal, and that's why we have chosen the symbol X for that subgroup. Now, if it is isomorphic to SL2 cross SL2, we remember that pi alpha and pi theta, this is the parabolically induced. This was the cuspidal for SL2, and we can take this external tensor product to get a representation of SL2 cross SL2, and then we induce it from this representation from X2 chain, and we call it this big pi alpha and big pi theta. Now, because these are simply induced representation, we can use Fabini's character formula to get these character values. To get these character values, and now this is the table that contains the relevant information. Now, again, the way we have constructed this, we don't know that whether these representations are irreducible, orthogonal, symplectic. We don't have any idea, but it doesn't matter that even if it is orthogonal or non-orthogonal, we can always take its symmetrization, that S of pi alpha, the one that when we take the representation and sum it with its dual and give it an orthogonal, the structure of an orthogonal representation. So we take these orthogonal representation, then corresponding to this, and by carrying out the calculation, this is what we get. These are the R pi, and S pi is always 0. And then Q is 1 mod 4, this R pi is again odd, and when Q is 3 mod 4, then this R pi for this pi, it is odd. And again, by simply expanding out the formula that we had for W of pi, we get the total Stiefel-Whitney class for these kind of representation have a formula something like this. and which implies that E1 and E2 both belong to H star SW of SP4Q, which gives us the equality that H star SW of this group is a polynomial algebra with two generators, E1 and E2. Now I think I'm up. The time is almost up. I would like to just show you how our formulas, general formulas for SP2 and Q looks like. So here we are working with these diagonal elements. Our character formulas are all use these kind of diagonal elements with the ones at the top and at the bottom, and in between there are 2i of minus ones. And here, as I said, for inside SP2N, we have this subgroup, which is isomorphic to indirect product of SL2Q. And we heavily use this subgroup for our work. And so we can project each of these to SL2Q and get these projection. And if you if you take the induced map at the level of cohomology, which is contravariant, and wherever it sends E, the frac E, which was the non-trivial element of fourth cohomology group of SL2, we call it EI. And the formula, the total Stiefel-Whitney class formula for pi for SP2N uses these EIs, and here this is this product using these mass frac I, and we also have expressed these again exponents in terms of these character values, and we also understand these coefficients as given as the coefficient below. So with this, I would like to here are the references where some of this is published work, and the one that I presented today is we have submitted it recently, and for the time being, you can find it on arXiv. And these are some of the other references. And thank you very much for your attention. And if you have any questions, please, I'll be happy to answer.
Thanks, Neha, for the wonderful talk. Any questions? So Neha, what could be some follow-up work which could be done in this direction?
Yeah, so obviously we don't have H star SW in general for SP2N. So one direction that we are trying to explore is this. So I'm currently working with Professor Urion at ANU to maybe something can be done there. And so another thing that can be that we can do is a combinatorial question, is to understand this. So what we know is that this is a symmetric polynomial in these EIs, but we don't know how to write it in terms of the bases, like if you simply take elementary symmetric functions. So how can we write it like that? So that is another question, but
I see.
yeah.
Interesting. Okay, if there is no other question, let us thank the speaker. Yeah, thank you, Neha.
Yeah, thank you very much.